Okay, this video is called Miss Missile Takes the Topic for Review Test. You're going to use this to understand anything that you haven't understood before. I'm going to go pretty quick, but that's because I didn't want the video to be way too long and 500 million megabytes. And here we go. Quick. Let's see. Once the solid has reached its melting point, how many minutes? So, minutes for melting. This is the fusion, the melting line segment. You want to know all the segments, study them all. It goes from minute 2 to 6, so that took 4 minutes. Okay, question 2. Increase in average kinetic energy. Average kinetic energy is the definition of temperature. So whenever the temperature is increasing, so is the average kinetic energy. So 2 has A, B, and C, D. Okay. Real quick, if you're going to memorize these charts, notice that there are 3 diagonal sections. There are 3 phases. The coldest is solid. The next diagonal is liquid. The hottest diagonal is gas. And then, of course, this is melting or fusion, and this is vaporization because you're going from liquid to gas. And this definition is super important. Number 3, pressure doubled, constant temperature. What happens to the volume? So the pressure is doubled. The temperature is constant, so I can ignore it. What happens to the volume? Well, pressure and volume have an inverse relationship. So they do opposite things. So if the pressure is doubled, the volume should be halved. Okay, this is just heat flow. Heat flows from things that are hotter to things that are colder, a higher temperature to a lower temperature. So you just got to get these all in Kelvin. The iron bar gains energy from the water if the temperature of the water is. Okay, so we want the water to be hotter than the iron bar, hotter than 325 Kelvin. So, I'm guessing it's the 65. The equation, of course, is right here. So I can turn them into Kelvin. .338. This guy equals 338 Kelvin. I bet this one equals 318 Kelvin. Not that it matters. This one is hotter than 325. Heat flows from the higher temperature to the lower temperature. Okay, see this definition? And also notice the word highest. Average kinetic energy is the definition of temperature, so we want the highest temperature. It does not matter, nothing else matters but the temperature. So it's that guy. 30 degrees Celsius happens to be the highest temperature. Ideal gas, the perfect gas. The particles are dots in space. They are very small in volume compared to the space around them. They're moving in random directions, straight line paths. They should not be attracted to each other. We wouldn't want to liquefy them because that would involve attractions. And the particles themselves don't have volume compared to the huge space between them. That's your perfect gas. That's your ideal gas. Okay, constant pressure. We're going to increase the temperature. Average kinetic energy of its molecules 2. Well, of course, it causes the average kinetic energy to increase because that's the definition of temperature. And also the volume will increase. So this is 4 because temperature and volume are directly related. That's Charles's law. Study your laws. Real gases most closely resembles that of ideal gases. Okay, here we go with the ideal gas again. We can act more ideal if they move fast Okay? Particles move fast because if they're moving fast, high temperature, then they'll collide with elastic collisions. They're more likely to collide with elastic collisions. They're less likely to stick together because they'll just like, bam. We also want them far apart from each other so that they are like tiny little dots with lots of space. So that would be low pressure, high temperature and low pressure. Moving fast and far apart is your perfect gas. Ooh, a cooling curve. So this is a gas. This is a liquid. This is a solid. The diagonal parts are still the three phases, but there's the hottest and there's the coldest, and everything's cooling down. Doo-ba-doo-ba-doo. Both liquid and solid phases are present. In this case, that would be freezing from liquid to solid. So 4. Okay, energy, ice to water, solid to liquid, melting, fusion. Okay, take the shape of a container. Could not be a solid. It could be a liquid or a gas, or I guess an aqueous would take the shape of the container too. This is the real difference. Completely fill. The only phase of matter that is going to expand to completely fill the volume of a container is a gas. Does not matter that it's NH3. All that matters is the little G label for gas when it comes to those properties. Doo-ba-doo. Combined gas law, or I could just think Boyle's law. This one I could just think it out, but please do notice that you have your combined gas law here. P1 V1 over T1, P2 V2 over T2. Temperatures must be Kelvin. Things can be crossed out if they're not used. Okay. Constant temperature. Boom, boom. He goes away. Volume of 2 liters, pressure of 1. The volume goes up to 4. So what we've got is 1 ATM, 2 liters. Don't know the second pressure, 4 liters. Or you could just think it out. The volume is doubled, so the pressure needs to be halved. Or just solve it. Half. Okay. I am not worried about sig figs for multiple choice answer, but if the answer is rounded and doesn't end up exactly what I think it's going to be, that might be why. It might be because of sig figs. This is an example of that. Okay. This is about joules of heat, absorbing and releasing heat. So, and the temperature is changing. So, here's our 3 heat equations. If the temperature is changing, I've got to use the MCAT. If it's melting or freezing, fusion or freezing, I'm going to use this one. If it's vaporization or condensation, I'm going to use this one. Even if they mention a temperature for these guys, if the temperature is not changing, I'm not going to use MCAT. Only if the temperature is changing. So this one is Q equals MC delta T. The mass is 10 grams. Capital C for water. I really, really, really hope you know where to find this. Capital C is specific heat capacity. There's no guessing here. They tell you what it is. Specific heat capacity of water is 4.18. Kelvin or Celsius doesn't actually matter here for a delta T. And you can tell the temperature goes down by 1 degree. So it really would be negative. You'd either have to put the negative here. Anyway, you get negative 41.8 joules. If you put the negative there, or you wouldn't put the negative there, but you would just think, oh, the temperature's going down, so it is releasing this amount of heat. You either have to use the word release or the negative sign, but they use the word release, but it helps you choose the right answer. They rounded it to 42 because of 2 sig figs. sublimation is solid to gas. Solid to gas. S's. Starts as a solid, ends as a gas. Okay. Energy is absorbed. Endothermic. Any phase change where you start lower and end higher. So it could be solid to liquid, liquid to gas, or solid to gas. Melting works. Solid up to liquid. This looks like volume of 150 milliliters at 300 Kelvin. Must be the starting temperature. I'm just going to write 300. The pressure is held constant, so I can totally ignore it. The temperature is doubled to 600 Kelvin. I don't even really have to think this out, right? What's V2? It's got to be doubled. Or crisscross applesauce it. Okay, ready? I'm going to sing it. Equal volumes of gases at the same temp and pressure have the same number of molecules. Amadeo Avogadro, that's his hypothesis. Melt, heat. This guy, Q equals MHF for heat of fusion. 35 grams. Heat of fusion, is it water? Yeah, it's water, H2O. Heat of fusion, boom, 334. I think it's the third one. Yep. So you're going to get 11,690 joules, but with 3 sig figs, it rounds to 11,700 joules. Okay. Release of energy means exothermic. It means that you start with more potential energy, you end with less. So you could go from a gas to a liquid, or a liquid to a solid, or a gas to a solid. Condensation works. Gas down to liquid would be exothermic. Liquid phase. The diagonal parts are the phases. The 3 diagonal parts, the coldest is solid, the hottest is gas, the middle diagonal part is liquid. What's the definition of temperature, people? Average kinetic energy. Ice melts. It's definitely not 0 Kelvin, because that's when everything stops moving. It actually could be any of these temperatures, 273 or 0 Celsius. Those are all the same temperature. But normal has got to use standard pressure. Normal has got to be one of these pressures, 1 atmosphere or 101.3 kilopascals. Definite geometric pattern, even though they're vibrating, it's got to be a solid. How are temperature and volume related? Temperature and volume of a gas are directly related, so if the temperature decreases, the volume also decreases. Okay. The pressure on a 3-liter sample of gas is doubled. What if I just put in 1 and 2? That's the pressure being doubled. 1.5, right? The new volume would be 1.5. Turn these all into Kelvin so that you can tell if they work. Okay, so this is 293, which means this is 303 313, 323. These Celsius temperatures are replaced with that. The only one that makes sense is this one. Heat would flow from something that's a hotter temperature to a colder temperature. Okay, see the change in temperature? Mass is 50 grams, capital C. And the change in temperature is 10. So what's 42 times 50? 2090 joules, which is about that. Volume and temperature. I think I've drawn this a few times already. Heat it up, it pushes the walls away to a larger volume. Okay, this is easy. If you put that in for the Kelvin temperature, not the Celsius. Okay? Kelvin is degrees Celsius plus 273. So make sure you put this guy in there, 418. 145 Celsius. And finally, there's a lot to read here. I do want you to read it all, but check it out. Time interval AB. Here's what's happening. It looks to me like the temperature is increasing. So, and it's about heat, right? So, Q equals MCAT. The mass is here. Capital C. If it were water, I'd say 4.18. It's not water, right? But look, they have to give it to you. If it's not water, they have to tell you. Yeah, let's leave this Kelvin, doesn't matter. Change in temperature. 30. Multiply 3 numbers. Keep 2 sig figs. To keep 2 sig figs, you round it to 710 joules. Okay, sorry it was a little bit messy and rushed, but I wanted to make sure I showed it all so that there are no questions. You're going to rock the test tomorrow.